About big data classification. Um, big data classification, as we have studied previously, that uh, we have some controllers in big data analytics. So, those controllers are observation features, and third one are classes. So, each of them have different sets of problems associated with them. Some problems or some challenges are common. For example, if we look at the storage or size, so this is common among the observations, features, and um, classes. So some problems are unique to them. For example, volume or storage or communication issue is unique to the observations. Similarly, variety is unique to the classes, and likewise, high dimensionality is the problem related to the unique to the um, features itself. So, if we look into the bigger picture, we can divide our whole process into three stages. I personally divide them into three stages. So, first thing, the existence of the data should be there. So, you need to collect the input data. So, once you collect the data, just remember this is not an ordinary data, this is big data. So, that means it has volume, variety, and velocity. So, once you collect the data, then it is taken as input to the process of big data. So, what is big data actually? So here, big data. In this process, we first want to understand our data, because in order to analyze it or mine it or predict or model it, we first need to develop some understanding related to data. So we understand the data by using different visualization tools. Sometimes we want to see, okay, if there are any incompleteness, inconsistencies in the data or not. So once you go through all this data, this process of understanding the data, you move on to shaping the data. Um, Not all the times you need data in the form of tables. Sometimes you need data in the form of just JSON files or some other structured format. So it depends upon what kind of analysis you want to put on later stages. And the second phase is technology. Once you have the data and you develop an understanding about the data itself, so you want to decide about the hardware or software resources you would like to use. So this is very crucial in analyzing the data, because for example, if you have image based data or video based data, so you will require some sophisticated technology, especially GPUs. Ordinary CPUs will not be sufficient for that purpose. So, depending upon or you may require some HPCs, like high performance computing clusters as well, um, or you can borrow these services from some cloud services. In either case, there are three main considerations to look after. One is storage, other is memory, and the third one is processing, which can be called as speed as well. So, processing, memory, and storage. These are the three requirements which you always consider while dealing with the big data. We are not talking about the normal data here. So sometimes you do have the resources for that. Sometimes you want to borrow for that. Some constraints related to technology are the size of the data itself. Um, your existing resources may not be sufficient, or the high dimensionality of the data. High dimensionality of the data is because this aspect of the data adds more complexity to the data. So this is very important constraint here. Um, and sometimes unavailability of the data. Unavailability means the data is maybe incomplete or imbalanced, or there may be some other constraint as well. So when you have data which is incomplete, suppose you are taking data from some online forms. So you can see that there are fields which you can skip, and there are fields which are mandatory. So the fields which you can skip or which are optional, somebody most of the you guys will skip those entries, and when you look at the data itself, those will be your missing values. So that means that you cannot take into account those values at all in your modeling process. So third phase, when you are done with both these phases, is the technique you want to use. So what kind of modeling you want to perform, and what kind of algorithms you want to use. So depending upon the technique you use, you get the output or desired output, and in this way you want to develop some understanding or some derive some pattern from the data. So this is the general overview of how big data can be classified into different processes through its life cycle. Then very important feature here is the how data versus big data correlates. We have done that, I guess, previously as well, but as we divided or classified our data into three controllers, which are features, observation, and labels or classes. So each one of them has different aspect to address. For example, if you look at the features, so features means dimensions. It defines the dimensionality of the data. So ordinary data doesn't have a high dimensionality, but big data has high dimensionality. So if we want to reduce its high dimensionality, so we don't want to take into account all the features. Instead, we want to take a subset of features and try to predict on the base of that those few features. Sparsity of the data is also very important. We will look in the coming test what is the sparsity. Basically, its concept is came from the sparse matrices, where you have a lot of zeros in your matrices. Um, then there is a subspace. Subspace means creating a subset of the data. Sometimes data as a whole is difficult to manage, and especially in terms of computing power as well. You don't have enough resources or computing power to process that data. So what you do is actually you create a subsets of the data. So it's just like you take a sample out of a population, and you can take different samples and execute them, and they will be quick to analyze as well, and will present you some useful insights into. So these are the issues or sorry differences related to features. Then there are differences related to observation. Before going into observation, I will first look at the labels or classes. Classes can be of three types. For ordinary data, it doesn't matter actually much, because the ordinary data doesn't have volume or variety or velocity at all. But when you are generating data at such an enormous amount, this becomes very crucial to handle. So the data can be imbalanced, inaccurate, or incomplete with respect to the number of classes it has. So there is example coming, so I will just skip the detail right now. Then related to observations. So when you are analyzing data, you are try to improve upon one thing or other. You may be trying to improve the accuracy or model itself or the algorithm itself, or trying to improve your mining process on different data sets. So each one of them can be classified into different types of processes. Either you are estimating something, approximating something, or optimizing something. So this is the all of these we will discuss in the coming text. So machine learning is the analytical part here, and whatever technique or algorithm you use, you have some common understanding or paradigms in machine learning. One thing is you divide your data into training and testing, and you figure it out on the basis of your, maybe on your experience or some previous published work, that okay, what percentage of data I need to slice for and keep it separate for the training, and for example 60% for training or 70% of the data will be for training and rest of the data will be for testing and validation. um, Other paradigm is cross validation. Cross validation is similar to dividing the data set into training and testing, except the whole of the data iteratively goes into training and into the testing phase as well. So what we do here in cross validation is that, for example, if we want to let's say go for five-fold cross validation. So we divide our data set into five equal parts. Train on four and test on rest of the one left. So it is leave one out strategy. So iteratively, you include the remaining four parts and include the leftover single part, and repeat this process for five times. In this way, whole of the data set is covered as the training and testing as well. So there is a method called early stopping. Early stopping is done when there is a chance of overfitting in your data modeling process. So you stop the process of training early so that it does not overfit and then go for testing or validation. Whether you adopt cross validation, training, or early stopping, from each of one of them, you go for obviously validation and testing in the end. So this is a machine learning paradigm. Okay, representation learning is a very interesting technique here. Representation learning actually um, it is useful for when you want to reshape your data and you want to understand your data. Basically, representation learning means these are the statistical techniques. So, for example, you use mean standard deviation, or maybe covariance. So these are the representation learning techniques. And similarly, when you try to draw pie charts, histograms, so these are all also representation learning techniques. So pie charts and scatter plots or box plots, these are visualization techniques, but their basics are coming from the statistics. They are not just in the air. So they are based on statistics, though. So they are statistical techniques. Similarly, same as to mean and standard deviation or variance or whatever you want to adopt. So those are also statistical techniques. So the use of statistical techniques and processes to represent your data, understand your data, or shape your data. When you draw a histogram or pie chart or box plot, you actually shape a data in a particular way. So this is representation learning. Okay, previously we have seen that when we have a data, we can apply some function on it, and that function can transform our data into some response or knowledge. So this is a general paradigm of the data. That, for example, when we related to IT as well, computer science as well, you say okay, data and information. So data is a raw fact, and when you process it, so it is converted into information. So similarly, here in big data, when we have a simple data, so we transform that data into some response set or knowledge. So each one of them have different characteristics, which actually we discuss in big data versus data paradigm as well. For example, when we talk about data domain, so its characteristics are dimensionality, sparsity, and subspace. When we talk about knowledge response set, it has the characteristics of imbalance, incomplete, and inaccurate. And similarly, related to mapping function or the function itself, we are trying either one of them, approximating, estimating, or optimization. So, just when we look at the classification model first, so this is a very good example of how class characteristics look like. Suppose you have two classes in your data. Ideal scenario is that you each of those classes must be have equal number of observations. But in reality, most of the times it is not the case. For example, when you look at the data of healthy and disease people or patients, healthy or patients data. So, and especially when you are focusing on a particular disease like heart disease, or heart disease also have certain types as well. So, in that case, the data of the patients or related to the patient is maybe if we look at the population of 20 million or 200 million. So in a 20 million of population, how many patients will be there will be of heart patients? So 1% or 2%. So that means the data itself is very imbalanced. So what are the disadvantages of such a data? That when you go into the modeling process with this kind of imbalance classes, like, so model will eventually learn more on the or train more on the normal data rather than the disease or patient data, because the number of entries are very low. So if I say okay 1 in 1,000, if the ratio is 1 in 1,000, so that means the ratio is so low, the number of entries are so small that your modeling process or algorithm can hardly take any feature from that particular entry into the modeling process. So whenever we try to predict something, ideally when you run some algorithm, you assume that the data or classes actually they are balanced. If you are looking for classifying oranges and apples, you always assume that okay both are in the same quantity. But if you are looking for classification between good apple and bad apple, both are apples. So naturally, you will say, okay, bad apples are lesser in quantity and good apples are more in quantity. So it's just like that. So there are techniques to balance such data so that we are not biased towards a certain class while building our model or making assumptions out of that data. Second is incomplete data. Incomplete data is very common when you are not placing any user authentication or some restrictions while collecting the data. If you are just relying on the honesty of the users to input all the data in a correct format, so that means that you are mistaken, and not everyone is honest in entering the data, and that results into inaccurate, incomplete data. Maybe some of the entries are completely missing, or they are completely inaccurate as well. So, for example, if in a names column, if anyone can put input number as well or special character as well, that means the data will become inaccurate. Or in the city column, if you are just taking the data in the form of numbers or any other thing as well. So, inaccurate data, I am not saying that all other data can be inaccurate. But yeah, there is a chance of 20 or 10% as well that there you have some inaccurate or incomplete data in your data set. So you most of the times we need to identify that data so that our modeling process or pattern recognition process doesn't uh, um, compromised. So okay, so error characteristics. Error characteristics are of three types: estimation, approximation, and optimization. So when you are deriving models on the base of two different data sets, when you are deriving models on the base of two different data sets, and there is a difference in the outcome of the model, obviously because of the data sets. So this difference is called as estimation error. This difference is called estimation error. You might have seen that people compare their results, experimental results, with some universal or state of the art method or state of the art data set. So in scientific experiment, it's very common that you are trying to trying to build a model or trying to predict something on the base of your data set. So, and you say, okay, we have achieved 90% accuracy, or we are, or these facts are coming out of these our data set. These are our findings. But you cannot claim it as such. You have to first compare it with some previous studies, some other data set which is commonly used or which is considered as standard in that particular domain. So we always have a control. This that set of data set or model acts as a control in experiment, so that you compare your result with the control of your experiment. Okay, so when there is a difference in data sets in a model building process, and obviously the um, outcome of the models will be different. So this is that difference will be the estimation error. What is an error, by the way? Error is the difference between actual and predicted. So here, when we are considering that, okay, one of the, one of our model on a particular data set is our actual, and the other one, which we are other model which we are trying to build on some other data set, is our predicted or model. So we compare our actual and predicted and see, okay, what are the differences, how much is the difference, and that difference will be our estimation error. Okay. Okay, next thing, approximation error. Okay, approximation error is when you derive the model on the base of different types of modeling processes. So modeling process can be widely speaking. There are some models which represent your model in the linear way, like linear regression is a very classical example. And some model building processes, they build the modeling in some non-linear way, like logistic regression. They normally build the model in the form of sigmoid curve rather than a straight line. So there are models which are linear and there are models which are non-linear. So when you have a single data set and you are building model, you are building a linear model and also non-linear model of the same data set. So obviously the outcome will be different for each one. So that difference is called as optimization error. Sorry, approximation error. So that difference is called as approximation error. And the third one is optimization error. Optimization error comes is calculated when you are actually trying different algorithms to build a model. For example, you are trying to build a particular linear model, but you are trying different algorithms to build same linear model. So the difference between the outcome in this particular scenario will be called as optimization error. So actually you will be seeing that which algorithm is more efficient than other. So in this particular case, we are not concerned with data set, we are not concerned with the linearity or non-linearity, we are only concerned with the efficiency of the algorithm itself. So in this particular case, we are actually trying to optimize, and the difference between the two outcomes will be optimization, will result in the optimization error. This is what is written here, and this is also described here in this particular figure. So how the particular modeling process works actually. So if you look at first, you have a model, whether linear or non-linear. So difference between the two is called as approximation error. Within each modeling process, you might have multiple algorithms that can be implemented to build that model. So each model, if this is your true model or your gold standard or whatever you say. So there is a best algorithm, and this is the algorithm you used or you built. Okay, to build this new model. So the difference between these two models is approximation error. The difference between these two algorithms is optimization. And similarly, the actual results. In the end, whatever algorithm you use, you will get some results, some accuracy or area under cover or any other measure as well. So you have some actual results and your predicted results or produced results. So difference between those two will be estimation error. So this diagram sums up the whole process actually, and this goes from here to from left side to right side as the figure shows. So you may not be confused that what is difference between the model, difference between the algorithm, difference between the results itself. Okay, data domain characteristics normally high dimensionality, sparsity, or subspace. These are the main characteristics in this particular you can say controller or classification. So just look at the this particular example here. Suppose you have three features. This is 2, 6, 1.1, 4, 8, 2.2, and 3, 7.5. If I just look at this, okay, these three features here: 2, 6, 1.1, 4, 8, 2.2, and 4, 3, 7. Okay, so in these three features, we have three columns. Each one of them have three features. There are three observations and three features actually. These are three observations and three features. Suppose we want to classify whether this is even number or odd number. So if you look at the third element of each observation, which is 1.1, 2.2, and last one is 0.5, does that count towards defining whether they are even or odd? Will that count? Not at all. So it will not matter that we whether we include this value or whether we skip that value. So what we can do is just go for selecting first two elements only. And this is very classic example of how we can reduce our dimensionality. We do not require every single feature in our dataset for classifying something, for predicting something, or making sense of something. So it entirely depends on the objectives of your analysis. Because here the objective was that I want to classify them as even or odd. If the objectives were different, then I would have selected whole data. But in this particular case, because my aim or objective was to classify them as odd, even, odd, so those third features were irrelevant in this particular scenario. So this is dimensional reduction or feature subspace as well. feature selection. Some people say feature selection as well. Similarly, this is in this particular example here. You can see there are a lot of zeros. There are three observations and similarly three features in each of them. But in each of the case, we have lot of zeros. There is one observation and there are others are zeros. So when we look at this, this is called as sparse data. So we have zeros in it. So it will make the modeling process more difficult for us because there is no data to compare with or no feature to compare with. So when we would go for how different features are correlated with one another, so zero will not count towards that. So when there is such a situation, you either want to recollect the data or want to consider that or there is inaccuracy in data or data is incomplete. So you go for completing the data. And if there are only fewer observations, suppose you have millions of observations and you have 1% of sparse data available there. So you either want to skip that data or there are other measures like you can put mean value or median value in place of zeros. So people do adopt such strategies to deal with missing data, or this is also called as can be taken as missing data. The data is missing. There is no data actually that should be there in ideal case. So this is sparsity of the data. So I will